How is Solana able to process tens of thousands of transactions in under half a second and do it all for a fraction of $1 per transaction? It's fast because of its architecture. Unlike other chains that scale by adding sidechains or sacrificing decentralization, Solana rethought the entire stack from the ground up. In this video, I'm going to break down 8 core innovations that make Solana one of the highest performance blockchains in the world. Solana's speed starts with proof of history, a cryptographic clock that records the passage of time by generating a continuous chain of SHA-256 hashes where each hash depends on the previous one. Since you can't skip ahead in this sequence and each step is computationally expensive, the hash chain serves as a verifiable timeline. When a transaction or validator vote is inserted into this sequence, it gets timestamped in a way that anyone can later verify, not by looking at the clock, but by checking its position between two known hashes. This solves a key bottleneck in distributed systems, agreeing on when something happened. Proof of history allows all validators to reference the same sequence of time without having to message each other or rely on synchronized clocks. That means Solana can pre-assign leaders, reduce coordination overhead, and still ensure secure, ordered execution of transactions. In short, proof of history doesn't replace consensus, it supercharges it by giving everyone the same trusted timeline to work from. With proof of history providing a reliable timeline, the next step is reaching consensus efficiently across thousands of validators. That's where Tower BFT comes in. Solana's custom consensus algorithm built directly on top of proof of history. It's based on practical Byzantine fault tolerance, a class of consensus algorithms designed to help distributed systems reach agreement even when some participants are faulty or malicious. In traditional PBFT, nodes reach agreement through rounds of communication and leader election, but this slows down as the number of nodes grows. Solana's breakthrough is integrating proof of history as a global cryptographic clock, allowing nodes to agree on the order and timing of events without constant messaging. This drastically reduces latency and enables high throughput across a large validator set. The key idea behind Tower BFT is that validators cast votes on the ledger's state at fixed time intervals, called slots, each lasting about 400 milliseconds. Once a validator votes on a proof of history hash, a checkpoint in the ledger, it's committed to that fork for a certain number of future slots. Each new vote doubles the timeout window to slots 4, 8, 16, and so on, making older votes increasingly irreversible. If 2/3 of validators vote on the same fork, that chain becomes final and cannot be rolled back. This mechanism ensures fast deterministic finality with minimal coordination overhead. But what if a leader fails to produce a block due to downtime, censorship, or malicious behavior? Tower BFT handles this gracefully. If a validator missed a slot, the network automatically advances the next leader in line. Validators track progress independently based on proof of history, so there's no need to halt or re-elect a leader. As soon as the next validator slot arrives, it can continue building the chain from the last valid state. This quick recovery process, backed by deterministic time and vote locking, helps Solana maintain high availability even when individual validators fail. Once consensus is in place and leaders are scheduled ahead of time, Solana needs a way to get transactions to those leaders before their turn begins. That's the role of Gulfstream, Solana's direct transaction forwarding system. Most blockchains rely on a mempool where pending transactions float around the network until a block producer picks them up. Solana takes a different route with Gulfstream, a system where transactions are sent directly to the validator scheduled to produce the next block, known as a leader. By avoiding the mempool entirely, Solana cuts down on spam, front-running, and network-wide transaction duplication. Since Solana pre-assigns leaders, one full epoch in advance, clients and validators can forward transactions straight to the right destination without flooding the network. This approach lets upcoming leaders begin validating transactions before their slot even starts, dramatically reducing confirmation times and memory overhead. Gulfstream allows Solana to handle a transaction queue of up to 100,000 and process tens of thousands per second. If there are temporarily more transactions that can fit into a block, a brief backlog is created, but with sub-second block times it's cleared quickly. This efficient flow keeps the network fast and responsive even during traffic spikes. To add prioritization, Solana introduced stake-weighted quality of service, giving higher transaction bandwidth to nodes forwarding through staked validators. Combined with Quick Protocol for fast stream-based networking, Gulfstream plays a central role in making Solana one of the only blockchains capable of matching real-world financial systems in speed and scale. With transactions forwarded to the right leaders, the next challenge is sending blocks to the entire validator network fast and reliably. Solana solves this with Turbine, its custom block propagation protocol, built to handle the enormous challenge of delivering massive blocks to thousands of validators fast. Instead of the leader node sending a full block to every validator, which would crush bandwidth, Turbine breaks the block into tiny packages called shreds and sends each shred through a tree-structured network. Validators are grouped into small clusters called neighborhoods, like local relay teams. A validator receives a shred, passes it to peers in its neighborhood, and sends some of it to other neighborhoods down the tree. This relay system dramatically reduces the communication burden on the leader and gets the block to everyone in just a few hops. But what if nodes are malicious or faulty? Turbine is built with adversarial conditions in mind. Each batch of shreds uses Reed-Solomon erasure coding, meaning a block can still be fully reconstructed even if many shreds are lost or dropped. Shreds are bundled into forward error correction batches, Merkleized and signed by the leader. So any validator can verify a shred's integrity even if it comes from an unknown source. And because the propagation tree is stake-weighted, validators with the most at stake are placed closer to the leader, minimizing the risk of misbehavior near the top of the relay chain. Turbine's tree structure ensures blocks reach all validators in about 2-3 hops, regardless of the total validator count. To add even more resilience, Turbine introduces randomized paths for each shred, determined by the shred's digital signature. This makes it incredibly difficult for attackers to predict or intercept enough of the network to cause widespread failure. In short, Turbine is what allows Solana to scale its network without breaking bandwidth or security. Now that blocks are being broadcast efficiently, the network has to process everything inside them. Enter Sealevel, Solana's parallel smart contract execution engine, and one of its most important breakthroughs. Unlike traditional blockchains, which execute transactions sequentially in a single thread, Sealevel can run tens of thousands of smart contracts calls at the same time, limited only by the number of cores on the validator's hardware. How? Because every Solana transaction explicitly declares which accounts it will read from or write to. Sealevel can safely identify non-overlapping transactions and run them side by side. Even transactions that only read from the same accounts without modifying them can execute in parallel. This transforms Solana from single-threaded global state machine into a massively multi-threaded one. Under the hood, Sealevel hands off instructions to a custom virtual machine based on the Berkeley packet filter, a fast low-level bytecode format originally designed for high-performance networking. Solana's version, called RBFF, is optimized for blockchain execution. Programs are stateless and live as executable bytecode, while accounts serve as the containers for state mapped by public keys. Only the program that owns an account can modify its data. This clear separation between code and state allows Sealevel to safely dispatch different programs and even multiple instances of the same program across available CPU threads or GPU cores. What makes Sealevel truly cutting edge is that when validators receive millions of transactions, Sealevel can sort them by program ID and execute the same program logic across many accounts simultaneously. Before execution, Sealevel simulates account access to avoid overlapping reads and writes, letting it sort and batch parallel transactions upfront. If thousands of users are calling the same contract, say a token transfer or mint function, Solana can batch those calls and run them in parallel, blazing through computation at speeds other chains can't touch. This approach unlocks unmatched throughput and scalability, making Sealevel a key pillar in Solana's high-performance design. So, Sealevel handles the smart contract logic, but transaction processing involves more than just execution. Solana isn't just fast because it reaches consensus quickly. It also has to process and validate thousands of transactions per second before the next block comes in. To handle this massive workload, Solana uses a technique called pipelining, just like modern CPUs. The idea is simple. Break transaction processing into smaller steps and let different parts of the computer work on each step at the same time, like an assembly line. Solana's custom pipeline is called the Transaction Processing Unit, TPU. It has 4 main stages: fetch, pull transaction data from the network; verify, use the GPU to check all signatures quickly; bank, use the CPU to update account balances and smart contract state; write, save results to disk and share them with other validators. Because each part of the hardware is handling a different stage at once, Solana can make progress on many thousands of transactions simultaneously. Even better, it works on affordable off-the-shelf machines. When a validator is the current leader, it uses the TPU to build new blocks. Other validators use a similar system called TVU, Transaction Validation Unit, to check those blocks. Both use pipelining to make sure nothing slows down while one batch is being written, another is being verified, and a third is already loading. This smart use of hardware is one of the main reasons Solana can support high throughput and near-instant confirmation times without needing supercomputers. But execution is only as fast as your storage layer allows. That's why Solana built Cloudbreak, a custom data structure optimized for fast, concurrent accesses to millions of accounts. As Solana scales up, storing and accessing account data becomes a real challenge. Traditional blockchains like Bitcoin and Ethereum don't have to worry much because they process fewer transactions. But Solana is designed for massive speed and parallelism, and that means its storage system needs to keep up. Putting all that data in memory, RAM, is too expensive, and using traditional databases like LevelDB is too slow, especially when thousands of users are interacting at once. That's why Solana created Cloudbreak, a custom-built database optimized for speed and scale. Imagine splitting up a huge library across dozens of shelves, where each shelf can be read and written to at the same time. Cloudbreak does something similar. It spreads account data across fast SSD drives and uses a clever system that lets many computers access different parts of it at once. It also uses a technique called memory mapping, where files are treated like RAM. This helps speed things up even more. Cloudbreak uses read and write sharding and memory-mapped files to allow many threads to access different accounts concurrently. Perfect for Solana's massive parallelism. Thanks to Cloudbreak, Solana can handle hundreds of thousands of transactions per second, even with millions of accounts. It's not a plug-and-play database. Solana had to build it from scratch, but that's the price for performance. In benchmarks, Cloudbreak can perform nearly 1 million reads and writes per second with just one SSD, making it one of the most powerful storage engines ever used in a blockchain. Solana handles real-time transaction processing efficiently, but what about the historical data? Unlike many blockchains, Solana doesn't require every validator to store the full ledger. Its account model is snapshot-based, meaning the current state of any account is always known at the latest slot, without needing to replay every historical block. As a result, validators and RPC nodes typically store just the last 1 or 2 epochs, about 2 to 4 days of transaction history. So where does the rest of the ledger go? Today, Solana's historical data is managed by a set of warehouse nodes operated by RPC providers, the Solana Foundation, and other ecosystem participants. But this system, while effective, isn't decentralized. Solana's long-term vision is a protocol-native solution called Archivers. Instead of relying on centralized infrastructure, the idea is to break the ledger into chunks, erasure code them, and distribute them to lightweight storage nodes. These nodes wouldn't validate or vote, they would just store historical data and respond to periodic proofs to verify they still have their assigned pieces. While archivers are not yet live on the network, their goal is clear: to make Solana the first blockchain to decentralize not just consensus and execution, but history itself. So, Solana's architecture is built on 8 core innovations I've just covered that work together to enable high throughput and low latency performance. Each of these layers was carefully designed to keep nodes busy, bandwidth optimized, and transaction finality fast, while relying on predictable leader schedules and synchronized voting rounds. But new projects and ideas for improvement are emerging to optimize Solana even more. For example, with the proposed Alpenglow upgrade, Solana could move away from synchronous voting and on-chain vote transactions. Instead, validators would vote off-chain in real time via a fast gossip protocol, only anchoring finalized votes on-chain. This reduces network congestion and latency while proof of history continues to provide reliable time ordering. Core ideas like Gulfstream and Sealevel would adapt to the more dynamic block production, and Turbine may evolve to handle increased fork propagation and more flexible confirmation paths. This shift could amplify Solana's throughput and resilience while preserving its signature performance. Validators will still rely on the transaction processing unit, Cloudbreak, and Sealevel to process and validate transactions at lightning speed, but under a more flexible consensus regime. While components like Archivist remain in development, the Alpenglow proposal signals a maturing ecosystem ready to address both scalability and decentralization in new modular ways. If this breakdown helped you understand Solana's architecture, give it a like and share it with others who are curious about how Solana works. Thanks for watching. Bye!